Hey, so the function I'm going to be working with is f of x equals x cubed. So I'm going to be using this graph to solve each of these components a through j. Okay, so if I look at the first one, part A is asking what are the zeros of f of x? And what that means is for what values of x, when you plug it in, do you get f of x is equal to 0? Okay, so for my function, I have x cubed is equal to 0. That is the f of x, setting f of x equal to 0. You may recognize this as actually the x-intercepts. And if you made that connection, if you were able to foresee that, congratulations. That's exactly what this is referring to. So the zeros of f of x are often called the x-intercepts or the roots or the zeros. So these are three common names that are associated with this action, this process of finding out the value of the when the function is equal to 0. And for us, since we're assuming x is a real number, the only value when you cube it, you get 0 out of it would be when x is identically equal to 0. So this is our x-intercept. Yeah. So that's pretty straightforward, and that's really nice. Which means then that the ordered pair 0, 0 is both the x-intercept and the y-intercept, which is nice for this function. Okay, all right, let's jump to part B. Part B is asking find the value for which f of x is equal to -1. So it's very similar to part A, except for now we have a different value. So we're looking for f of x equal to -1. So if we plug this in, I'm looking again for when does x cubed equal to -1. Well, I can solve this a couple of different ways. I can take a cube root directly, or I can factor out. I could have this over set it equal to 0 and then try factoring it. Uh, so there's a couple of different ways to solve it. So I'm going to show those two methods just to kind of give you some different options here. So the first one is to take just the cube root of this, and that definitely gives us one solution. So this, because this is the cube root, it's not a square root, this actually gives us then the value that the cube root of -1 is -1. Um, and one way you can see that is -1 times -1 times -1. That's -1 cubed, right? Because this -1 times -1 is +1 times -1 gives you a -1 again. So it's a perfect cube, and so the cube root would also be -1. So that checks out. If we add this over, we could write this as x cubed plus 1. And then we recognize, oh, look, that's a perfect cube, and x cubed is a perfect cube, and 1 cubed is a perfect cube. So we can actually factor that as x plus 1. And then this is a special factoring rule. This is x squared. This is x plus 1, x squared minus an x plus 1. Okay. And so this, we could see if it factors, or we can see if the quadratic formula allows us to solve it. So this is opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Since the discriminant here is 1, this is a positive 1, minus 4, this actually is less than 0. So this doesn't have any x-intercepts. So this doesn't, at least not in the over the field of real numbers. And so the only possible solution is when x plus 1 is equal to 0. And so this factor is, so if we set x plus 1 equal to 0, then we would just solve, and then it gives us then x equals -1. So it's kind of a roundabout way of getting to the solution. However, the fact that it's a factoring process where there may have been additional solutions coming in. So either works, and both get us there. And I think for the sake of ease, the cube root is probably the most direct, but understanding the factoring is a good skill to have. Okay. All right. Part C says find all values for which f of x equals -2. Okay. And so this is very much the same sort of thing as part B. So we're just going to have x cubed in my case equal to -2. And so x, if I take the cube root of -2, that is in fact the answer. And so that's an irrational number. There's the decimal approximation stuff. We'll leave it in that form. All right, part D ask is f even, odd, or neither? Well, if the definition of an odd function means that if f of x, if we replace x, f of negative x, if we replace x with negative x, and that equals negative f of x, then the function is odd. That's the definition of what it means to be an odd function. If f is even, then f of x becomes, when we replace x with negative x, then it just becomes the same as f of x. In other words, in an even function, it's like absorbing the negative, right? So it's not unaffected by the negative sign. And if if the negative comes out inside when you replace x with negative x, then that's a definition of an odd function. And then neither means that it doesn't have either of these properties, right? So that um, it gets kind of just nothing of the sort with the negative kind of comes out. Okay. So actually most functions are neither. But let's take a look at our function here. So if we replace x with f of negative x, let's see what that does. So I'm going to replace, this is going to be equal to negative x cubed. Well, that's negative x times negative x times negative x. That's what the cube means, right? So I have a negative times a negative x. So that gives me a positive x squared times a negative x. And then if I multiply these two together, I get a negative x cubed. The like bases add the exponents and I get a negative here. Well, x cubed is f of x. So this is negative f of x. So it looks like when we replace the negative x, we end up getting negative times f of x. So that's the formal proof that this is in fact an odd function. So x cubed is an odd function as we would expect. And this is the proof of that example. Okay. All right. Now let's see. Does for E, does f of x have an inverse? Okay, so if it has an inverse, that means this is the notation for f inverse. This is not 1 over f. It's not a negative exponent in the sense of like 1 over something. This is just the inverse notation. And so what does it mean for f inverse to have a function? Well, if I just kind of look at the graph of f of inverse, we saw earlier in week 1 that if I draw vertical lines, that tells us the VLT tells us f is a function. Okay. If we look at the horizontal line test, the horizontal line test says that if my horizontal lines intersect the function at most one time, then f inverse exists. Okay. So we have to apply the horizontal line test to our function in order to determine whether or not the inverse exists. Mathematically, what this is saying is that the function is 1 to 1. Okay, so if the function is 1 to 1, then we would say that that it has an inverse, that the inverse exists. So another way to show this algebraically, if you don't know the graph of the function that you have, or if you're not really sure, or if you want to be more precise, then to show something is 1 to 1. Okay. You assume, let's say you have f of a equals f of b, where a and b are just some numbers in an interval. You assume that this is true, or if this is true, this is only true if a is identically equal to b. In other words, okay, so if this, then this. Okay, so if this is true, then this is true. So to show something is 1 to 1, that's what we're going to do. Okay, so let a and b be real numbers, be elements of the real numbers. Okay, and then so we have a cubed is equal to b cubed. So this is f of a equals f of b. Okay, that implies then that a cubed is equal to b cubed. Okay, and so we're going to try to solve these. So if I subtract over this is going to be very similar to how I set this up here. We're going to treat it more formally than just taking the cube root of both sides. So this is a cubed minus b cubed. And a and b are arbitrary, so it doesn't matter which one is which. We're going to assume that possibly a is greater than b if they are different. And this is going to equal to 0. And then factoring this, we get a minus b times a squared minus ab plus a squared. That should be b squared, sorry. And that should be a plus there. Okay. So this factors. This does not factor. This is something. So there's no x-intercepts here. So this implies then that the only way that this could equal 0, because remember before it was equal to 0, the only way that this could be equal to 0 is if a equals b exactly. So this is in fact 1-to-1, which does show then that f inverse does exist here. Okay. All right. So that's part E. F we want to show is F0 a max, min, or neither. Let's go ahead and jump into that. So if we look at, and that this is, what are we on? F. Okay, so we want to know if F0 is a max, a min, or neither. Okay. All right. So, and this is, we're talking about a local max here or a local min. It could be that a local max or min could be a global thing. So if we look at what does that mean, kind of think of like a little bit of a step to, we do, or we may know that the graph of x cubed looks like that. And so like this is the value of f of 0, right? This is x equals 0, and it happens to actually equal 0. We saw earlier that the y-intercept and the x-intercept are the same. And so we're looking to see, is this a max, a min, or neither? Well, if you think about it, if we take a small step to either side, what do these situations mean? Okay, what's a local max or local min look like? Well, a maximum is like climbing to the top of the hill, right? So if it's a local max, what we would expect is that we're kind of coming up, we're climbing to some values. So if we step to the sides in either direction, you're kind of like stepping away. Your y values are getting less, right? So when you're here, you're at the top of the mountain, right? You're at the highest peak. And so if you step to the left or to the right, your y values would be decreasing from that. And if you look here, you're seeing that it's decreasing to the left, but it's not decreasing to the right. So that means that that is actually not a local max. Okay, so what would the local min? What would that look like? Well, the local min means it's at you're at like the bottom of the hill, right? You're at this little valley thing here, which means that if you step to the left or to the right in either direction, that you should expect if you're at a local min that your f values or your y values are going to be increasing. So they're going to be a little bit taller than you, which is what we see here on the right side. If we step away from x equals 0, we are increasing. So it looks like it's a local min here. But when you step to the left, we're actually decreasing in our y values here. So it's neither that it's going to be increasing or getting less than, it's getting less than all the way through that interval. So it can't be a local min. And so in fact, what is it? Well, it's increasing to the right, it's decreasing to the left. So this at our function, we're going to get that it's neither because it's not doing this, it's not doing that. It's actually doing both of these. So in our case, we got neither. All right. Let's see. Oh, and what you can do to calculate this explicitly, if you don't have a picture of this, is just take a little. So f of 0. So try like f of 0.1. Okay, and then compare that to f of 0. And so that's a little step to the right. And you can see which direction is it getting bigger or is it getting smaller than your f value of f of 0. Okay, and then try f of like negative 0.1. Okay, and so you're stepping to the left and to the right here at negative 0.1, 0.1, and then f of 0. So evaluate it at those 3 points and see what values it is. Is it doing this? Is it doing that? Or is it going to be a neither? So that's how you would check out what's happening here with the function and its extreme. Okay, looking at G here, we want to graph f of x, oops, plus 1, and then we're going to subtract 1 from it. So we're going to learn here, how do these parameters here shift our graph around? Well, f of x looks like, for us, looks like this. And so what am I doing here when I plug in f of x is equal to x cubed? So when I plug in x plus 1, I'm getting x plus 1 cubed. So what is that doing? Well, if I think of like a negative 1, if I plug that in, that makes this 0. So this point here kind of shifts it to the left uh, by a negative 1 unit. So it's going to look close to exactly the same thing. It's just shifted to the left. So the positive one here actually shifts it to the left, minus 1. Okay, and then let's consider the minus 1 here. So I'm just subtract. So whatever this y value is, it's just going to subtract 1 from it. So it actually shifts this graph down 1. Okay, so then I'm going to shift. So it's minusing 1 to the left, and then it's subtracting 1 to the left, and then it's subtracting 1 from the y values down. So it's actually going to just be something like that. Okay. So this, so the minus 1 then at the end of it shifts function down 1. Okay, so it's the original. So if I was to put these two together, my point was at 0, 0. It's been shifted down 1, or to the left 1 and down 1. So that's where the value is. And so it looks like our new function is going to look like um, something like that. All right. Moving on from G, let's look at H. So H is wanting us to graph the function h of x. I guess this was what we call g of x, this shift of these two things. Okay, so let's graph here. Anyways, h of x is equal to, looks like we're scaling it by 1/2, and then we're scaling the inside by 1/2. Okay, so let's see, how does that affect this graph? So f of x is equal to 1 is equal to x cubed. So I'm replacing x cubed, or x, with 1/2 x. So this becomes f of 1/2 x is going to equal x over 2 cubed, which means it's going to be x cubed over 8, because 2 to the third is 8. Okay, and then let's see, what else do we have here? Okay, um, so after that, we're going to multiply that by 1/2. So we have 1/2 of x cubed over 8 makes this x cubed over 16. So if we think about the original function um, like this, now we're going to divide it by 16. So if this number was 1, it's now going to become 1/16th its value. So the shape of the graph is going to be scaled by 1/16th, meaning it's going to keep the same shape, but it's going to be, you can think of it as kind of like flattening it out, or rescaling the y-axis so that it's a 16th is less, or 16th fewer. So it's reducing the value. So the shape will be the same, but if you keep the same zoom, then what the appearance will look like is it's flattening out the graph, because you're making it so much smaller. So I can show that this way. So if this was, I should have drawn a little bit more carefully there, but for example, this is 1, because 1 cubed is 1, and then 0, 0, and then so that would be -1. Okay, so if I'm looking at these 3 points, this is x cubed, right? This is the original one. Okay, so in the if I rescale this to 1/16th and -1/16th and 0, then that's the same thing as f of x. So it has that same shape. But if I don't, then that means that this 1/16th, well, it's going to be 16 up here. So the actual y value would be off the page here. So so you can see that really all this is doing is it's flattening out the curve, but it keeps the same shape if you rescale the axes to match the same So I hope that makes sense. But you'll see that it's reducing the values by 16. So it's significantly reducing the overall value. Um, you won't notice that out at like 1,000 because 1,000 cubed divided by 16 is not going to be as significant as at like 1, for example. But it still significantly affects the graph as flattening it out. Okay. All right. I is what's going to happen if r of x is equal to negative f of negative x. And then I add 1 to that. So let's play around with this. So f of negative x is going to equal negative x cubed, which we already saw is the same thing as negative x cubed. So what does that do? Well, if this is my actual x, then where it's positive here, I'm multiplying it by a negative. So it's going to shift it. And where this was negative, that becomes positive. So it's going to be moving it over there, like so. Okay. So it has this kind of like flipping about the y-axis process. So that's this first negative. And then look, this negative here, well, that's just saying go back to where you started from. So if this is negative, then this negative is going to switch it right back to where it started from. So this is f of negative x, and then negative f of negative x. What does that do? Well, it shifts everything right back to where it was. And then next, we're going to add 1 to it. So we're just going to take this graph and shift it up 1. So there's the plus 1. It's a shift up. So in net results for this graph, r of x is just a shifting up of f of x by 1, since it's an odd function, so the negatives cancel out. Is another way of thinking about it. So it just shifts up the graph 1. So other graphs, it'll make a much more significant impact, just depending on what type of function you have. Okay. All right. So that's I. And then last but not least, we have J. And J is a really cool problem. So J, it's asking find the average rate of change for when x1 equals -2 and x2 equals 1. Okay. So the average rate of change has many names. The average rate of change is also called the slope of the secant line, or you may notice it as just the slope. And what is this? This is the change in y divided by the change in x. And so oftentimes we designate change by this triangle looking thing. It's called a delta. So delta y over delta x. This is representing change in y over change in x. And so for us, that's going to be the f of where am I going from? 1 minus where am I coming from? I guess I should say going to, and where am I coming from? So f of -2. So this is the change in y values. So f of 1 minus f of -2. And then down below, they're going to match up. So minus -2. So 1 minus -2. Okay. So I need to evaluate f of 1 and f of -2 in this. So f of 1 is going to be 1 cubed minus -2 cubed divided by 1 minus a minus makes that a plus 2. And then finally, we have 1 cubed is 1. 2 cubed is -8. -8 plus, or -8 times a -1 in front, or these double signs cancel each other out. And so this becomes 1 plus 8 over 1 plus 2, which is 3. 8 plus 1 is 9 over 3. And so this then just reduces to 3. So the slope um, of the secant line, the average rate of change, or the change in y divided by change in x has a value of 3. What that means is that if you're looking at the y value from negative, let's see, -2, -8 to 1, comma 1, if you look at the change in this value between these two values, for every step you go to the right, you're climbing up 3 units. So if this is at -8, then this would be at -1, comma -5. Okay, and then if you look at one more to the right, so then this would be at 0, and then coming up, this would be at -2. And so you can kind of see as you plot along, this is saying that the average rate of change is as you step to the right 1 unit, you're increasing by 3 units until you get to 1, 1. Okay, so that's the average between those two. Okay, I think that's all of the points for this problem. So you're going to match your problem with a very similar thing. So the last thing I'm going to do is jump over to some technology and show you how you might be able to use these ideas and maybe get a little bit more insight and a little bit of more play in that. So I'm going to pause here and jump over to some tech and we'll have some fun. So I'm going to invite you to explore geogebra.org. So if you just type in geogebra.org, you'll come to a landing page that looks like this. And the button we'll want to click on is this one right here where it says Start Calculator. So we'll jump there. And that's going to open up a calculator app, if you will, that looks like this. And you can download these for your phone and mobile devices, or just keep them on access on the web. So there's lots of ways to get here. It's very similar to Desmos. I actually love Desmos, but I haven't used it as frequently. And I find like this actually has a lot more both functionality and purpose or usefulness. So I've been spending more and more time here on this one. So let's walk you through how to use this tool to solve ours. So whatever your function you have, mine is x cubed. So I'm going to type that into my thing. And if I hit that in, then I get my f of x is equal to x cubed. And so the nice thing is that this kind of helps you go through a lot of these problems uh, very effectively in exploring this. So for example, you can actually click here and get a table of values. The one that's really helpful here is the special points. If you click on that, it'll tell you if there's an extrema, it'll tell you where it intersects the axes, and it'll give you the roots of it as well. So the root here is the answer to part A, where it's asking for the zeros. Remember I said that one of the words that they use there is roots, and so it tells you that the x-intercepts here are at 0, comma 0. It also tells you here that that there is no extremum, so that answers which question is that? F asks if there is f of 0 in our case is, and in this case, it's not an extreme. It doesn't know. It's another way of saying neither. So having the calculator do the work for you is good, but you need to understand what it's telling you. That's why we went through that first part. So then we can do part B. It asks for find the values of f of x equal to -1. So here you can just hit y equals -1. And so if you look there, you get the function y equals -1. And if you look here, it tells you where those two intersect. Okay. So it's at x equals -1, you get the y value of -1, and that's exactly what we saw. And that's the only place it intersects. So that's our only solution. Likewise, doing part C is just as easy. So we're going to say y is equal to -2. And hitting enter there, we get the point of intersection there is at this negative value. So this is that irrational number that we were talking about, which is the cube root of 2. This is what it looks like as a decimal. So again, you can get an answer here, but you need to know what it's saying, right? And it's form. So that's really cool that we got those first two. So we've already answered A through C. Is D? D is asking if it's even or odd. Okay, so you can type in f of -x and hit enter, and you can see what it does. And so it actually shows you the reflection of that process, which is actually related to what we're going to be doing later. And you can see that this is indeed the opposite, or it's the reflection of this. And so again, understanding that this negative comes out, you get to see visually that it's a reflection, right? It flips it, which would be negative times f of x. So you know that this is an odd function. Does f have an inverse? Inverse of f. Inverse, that was an inverse function. So this one, you might have to do a little bit of work, but you can say f of a equal f of b, and it says true if a equals b. Do you see that? So it actually tells you then that this is one to one. So a and b are just arbitrary constants that it created scalars for, and the only way that it would be true is if this was equal. Otherwise, you'd have these scalars, and you could probably pull them back and forth to see if they ever equal each other. But it tells you right away that in fact it is true, which means it does have an inverse. We've already answered part F, since it is neither. That was coming up with the extreme part here, so that was answered right away. Part G and H and I, GH and I are where this was really, really helpful. So we can actually type those in. So x of x plus 1 minus 1, we can plug that in and you can actually see what the graph q of x in this case does. Let me shut off the other ones here, just to make it a little less confusing. And I'll shut off that point there. And so you can see Q here is the result that we were looking for in part G. And then we can look at h of x. So h of x was 1/2 times f of x over 2. And so this is what I was referring to earlier, that it has the same shape, but the reason why it doesn't look like it here is because we've kept the original y-axis. But if we rescaled these to be divided by that 16, then it would have exactly the same shape as the green one. It's just that the y values would be significantly smaller. So this is that double scaling, and you can actually see what the function is here. It's x cubed 2 to the third times 2 in the 1/2. So that's 8 times 2. That's the 16 that we're talking about. Okay. And last but not least, oh, it's almost the same. R of x here, negative f of negative x plus 1. As I mentioned earlier, this is that s of x here. So that s of x is exactly the same thing as the f of x. It just ends up shifting it up 1, as I was mentioning, because the double negatives here, f being an odd function, they cancel each other out. So this is essentially just really being x cubed plus 1, because that's why it's a shift up as we expected. And then last but not least, you can compute the j value, finding the average, by literally just plugging that in. So f of 1 minus f of negative 2. And then you can divide that by 1 minus a negative 2. So plugging that directly in, it actually computes the value directly for you there. 3, which is what we got in our calculations. So this technology, GeoGebra, can be very helpful in being able to make sense of these problems and actually be a visualization of the problem that you've been working on, and maybe make it a little bit more accessible or a little bit easier to understand and to be able to answer these questions. Okay, I hope it was helpful, and I wish your team all the luck with your problem and being able to explain it to the group. Okay, all right, take care of yourselves, and I'll see you in